All right, everybody. Hope you're having a great Monday today. I'm just going to tell you the plan for this week. So on Tuesday, we're going to have a review day for Unit 2. And then on Thursday, we're going to have our unit test. Okay, so your assignment for today is going to be to watch this video where I'll be reviewing some of the stuff we've learned. And then to complete the practice test, which is online. So the practice test is not the same length as the actual test. The practice test is 34 multiple choice questions on AP Classroom. If you can't access AP Classroom, I've included a PDF as well. And you'll complete those. Tuesday, we'll spend reviewing any questions that you have from those 34 multiple choice questions. The actual test itself will be 20 multiple choice questions followed by a free response question. The free response question will be the exact same free response question that you've already seen and that we've worked through somewhat. So if you want to access that again, that's also on Google Classroom. There's a PDF of it there. Okay, so without further ado, I'm going to review some of the stuff. I'm going to start off with derivatives and integrals, then the relationship between position, velocity, and acceleration. And then I'll walk through one type of integral problem that we haven't really gone over, but which will be important. Okay, so first things first, I want to go over some notation for keeping track of powers with variables. So if we've got a term like, let's say 6t to the third, that's got the power very visible, right? But if I write 6t squared or 6t to the 1 or 6t to the 0, there's some shorthand that you might see sometimes, okay? So instead of saying 6t to the 1, they could also write just 6t. So if you see a variable without an exponent, that means it's to the first power. If you see a variable to the 0th power, that's the same as just 6 times 1 or just 6. So if you see any constant, you can imagine that that is a number times a variable to the 0th power. Okay, so now we're going to move on from that. Let's go over derivative. So let's say that my function is, I've got a function of t that's like 6t to the third minus 2t squared plus 7. Okay, so what this tells me, in order to do the derivative of this, I'm going to have to use the power rule. So for that, I'm going to take whatever variable is out front, I'm going to multiply it by the whole term, and then I'll decrease the variable by 1. So the derivative of f with respect to t, I would write it like this, is going to be, I'm going to take 3, all right, and that'll be times the 6t, and then I'll make it to the second power instead, minus 2 times 2t to the first, plus 7, this would be 7t to the 0th power, and so I'd have plus 0 times 7t to the negative 1. 0 times this whole thing is going to be 0. So if you ever have a constant, you're taking the derivative of it, it's going to go away. So my derivative of this would equal 3 times 6 is 18t squared minus 2 times 2 is 4t to the 1, or I can just leave it as t if I want to. So that would be my derivative. Okay. To do an integral, that's the opposite of this operation. Okay, so instead of multiplying the term by the exponent, so instead of taking 3, multiplying it by it, and then decreasing the exponent by 1, I'm going to do those steps in the reverse order. So I'm going to add 1 to my exponent, and then I'll divide by that number. Okay, so if I want to call this, I'll call this g of t is equal to that. All right, so if g of t equals this, and I want to get back to f, I can do the integral. So I can say that f would be the integral of this thing. So again, an integral, this dt, so the integral way you write it is you'd write this fancy s, you write your function, and then you write d and then some variable. So this would be integral with respect to time, just like we do the derivative with respect to time, similar to that. Okay, so to do this, I'm going to undo my operation there. So I'm going to add 1 to my exponent, so that would be t to the third, and then I'll make this term be 18 over 3, right? Because that's my exponent. Okay. For this one, minus 4, instead of t to the 1, I'm going to make it t to the 2, and then I'll divide by 2. Okay. And then I've got to add some constant at the end, okay? Because I don't know if there was a constant at the beginning, that would have gone away. So the way we indicate this is we're just going to say plus c. You don't have to worry too much about that. Okay. So if you don't see that in an answer, that's fine. The simplified form of this would just be 6t to the third minus 2t squared plus some constant. We can see that this function is the same as our original function. So when we do a derivative and then an integral, it undoes it. Okay, derivatives in integrals are important because they help us understand the relationship between position, velocity, and acceleration. Okay, so I'm going to write this as position, velocity, and acceleration. To get from position to velocity, we're going to take the derivative with respect to t. So we go derivative with respect to t. So we do dx over dt. To get from velocity to acceleration, we're going to take the derivative again. So derivative of velocity with respect to t. Okay. What this means is that the velocity is telling us how much the position is changing over time. All right, so it might tell us that the position is changing by 5 meters each second. That's why velocity is given in meters per second. What acceleration tells us is how much velocity is changing over time. All right, so if we've got 5 meters per second squared, that means that every second our velocity is changing by 5 meters per second. Acceleration does not have to do with how fast something is going. That's what velocity is. So this is how fast something is going. This would be how speed is changing. Technically, it's how our velocity is changing. So it could be a negative number that's increasing its speed because the velocity would be going negative. Okay, to go backwards, we could do the inverse of deriving. That would be the integral. So we'd say that the acceleration, or the integral of acceleration with respect to t, would give us velocity. And to get to velocity for position, we'd take the integral of velocity with respect to time. That would give us position. Okay, so this is equal to velocity, this is equal to acceleration, this is equal to velocity, this is equal to position. So this would be equal to x. That's an x there. Okay, cool. So that's all that. All right, next I'm going to go over the way we get one of our kinematics equations from calculus. So let's imagine the following problem. I'm not going to write out all the words for the problem, but I'll write out our assumptions for it. So I'll do this right here. Okay, so let's say that we've got a problem of me dropping a rock, or actually me throwing a rock down off of a cliff. Or no, I'll throw a rock up off of a cliff, and it'll go up in the air and then it'll come back down. So for my assumptions, I'm going to say that, let's say I throw it with an initial velocity of 8 meters per second. Let's say that the acceleration, because it's in the air, the acceleration of anything is negative 10. So it's 10 meters per second squared towards the ground, so that'd be in the y direction. Our acceleration in the x direction would be 0. And so acceleration in the y direction, we'd say is negative 10 meters per second squared. I'm just going to do this problem in one direction. So I'm just throwing it straight up, and it's going to go straight down off the cliff. All right, I'm going to say my initial position is equal to 200 meters in the air. All right, my picture for this, I'll draw the ball is going to go up in the air, and then it's going to go down like that. Okay, if we're asked to find a position of this at a given time, I can use these relationships to come up with the formula that we've been using in class. So I know that my acceleration is equal to negative 10. Okay. If I want to get my velocity, I do the integral of acceleration with respect to time. So the integral of negative 10, or a dt, which is the same as the integral of negative 10 with respect to time. Okay. If I take the integral of negative 10 with respect to time, that's equal to negative 10 times t to the 0. Remember, any number just by itself means that number times t to the 0. So this is the same thing as, let's go negative 10 t to the 0. To do my integral, I have to add 1 to my exponent, so it'd be t to the 1, and then divide by 1. So this would be negative 10 t to the 1 over 1. Okay, this means my velocity function is going to be negative 10 t to the 1, I'm not even going to write that, divided by 1. Okay, so divided by 1 doesn't mean anything. So my velocity function would be negative 10t, and then I've also got to add in a constant there, which would be whatever velocity that was at time t equals 0. Okay, my velocity at t equals 0 is 8 meters per second squared. So to get my velocity function, I'm going to get negative 10t plus 8 meters per second, so plus 8. You'll notice that this is the same form as our, I think it's our second, whatever it's called, our second kinematics equation, but the one that says that our velocity is equal to our initial velocity plus acceleration times time. So we get that if we integrate acceleration, that's automatically the form that we get. We get a times t plus whatever constant we had at the beginning of our problem. Okay, if I want to find the position function, I'd do the same thing. So position is equal to the integral of velocity with respect to time, which is the integral of negative 10t plus 8 with respect to time. Okay, so now I've got to take the integral of this function. So I'm going to increase the exponent here by 1, so that'd be t to the 2, and then divide that term by 2. So I get x is equal to negative 10t to the 2 over 2, plus this would be 8t to the 0, so that would become 8t to the 1 over 1. So plus 8t to the 1 over 1. I don't even have to write that. And then plus c. That constant here is going to be whatever my initial position was. All right, so just like this one here was v0, we're going to add in x0. Here. So x0 would be 200. Okay. Now, if we look at this equation, what we can see is we've got our final position is equal to our initial position plus our initial velocity times time plus 1/2 of our acceleration times t squared. Okay, so that is where we get this function here. So this thing just comes from our definition of an integral and of a derivative. So our position is equal to our initial position, that term, plus our initial velocity times time, so that's v0t, and then plus 1/2, so that's the over 2, our acceleration times time squared. Okay, so that's how we get that first kinematic equation. That's how we get our, I think it's either our second or our third one. Okay, let me check, see if there's anything else I wanted to go over. Oh yeah, so there's one more thing I want to go over in this video. So that'll be a certain type of problem that we haven't quite seen before, but that we can use given what an integral is. So just like in terms of graphs, derivative is the slope of a line, and an integral is the area under a curve. Okay, so we've done some problems where we've looked at the slope of a line of a graph. We're going to do one that involves looking at the area underneath the graph. Okay, so here is a question on the practice test. This says the graph above shows the speed v of a car on a horizontal road as a function of time t for 12 seconds. Distance traveled by the car during this time interval is most nearly what? Okay, so they've given us a graph of velocity times time, or by time. First things first, I'm just going to go over like what is this graph showing us. So this is saying that at the beginning, it's got a velocity of 0. When our timer says 1 second, it's got a velocity of 5 meters per second. At 2 seconds, it's got a velocity of 10 meters per second. That means this car is speeding up for the first 4 seconds here, and then it's going to be continuing at the same speed for the next 8 seconds. All right. If I want to get position, and I've given the velocity, so I've got the velocity of the car at any time, and I want to find position, the way I do it is I take the integral. So if I've got velocity, I'm trying to get to position, I'm going to take the integral. The integral on a graph is the area under the curve. One way of thinking about this is like if I go for 1 second, let's just like look at this last part here. So if I move for 1 second, let me see if I can draw. Here we go. Yeah, I can draw. Yeah, okay. So if we look at this last second here, we do 1 second and we're moving at 20 meters per second, okay? So our distance is equal to 20 meters per second times 1 second, all right? We can think of that as like a little rectangle here, okay? If we're doing, so this rectangle has a height of 20 and a distance of 1. So that area would be 20 meters per second, okay? The previous second, it also went 20 meters, right? Because it was moving at 20 meters per second for another second. Okay, to get the total amount of distance that it covered, so this is another second where it's going 20 meters per second, so that would be 40 meters per second. To get the total amount of distance it covered, we'd have to take the area underneath the curve. All right, in order to do that, I'm going to break this up into 2 different shapes, right? Because I know how to do the area of a rectangle, and I know how to do the area of a triangle. Okay, so for this portion here, we've got 8 seconds where the car is moving at 20 meters per second, right? So 20 meters per second for 8 seconds. In order to get the area there, we get A is equal to 20 meters per second times 8 seconds. That means it would go a total of 160 meters in that time. Okay, for this other portion of the graph right here, it's moving at a varying speed, okay? So in this first little part, we can think of this as breaking it up into a lot of little rectangles that we're just gonna add together, okay? But the important thing is that if we find the area under this, we'll get how much distance it's covered because it's a velocity versus time graph, right? So if I take the area under the curve of velocity, I'm gonna get position. If I take the area under the curve of acceleration, I'll get velocity. Again, taking the area under a curve is the same as integrating. Okay, so I gotta find the area under this triangle here. All right, so my base for a triangle, the area is equal to 1/2 base times height. That's given on our formula sheet if you ever forget that. You can also think of it as just find the area of a square and then divide that by 2. Okay, so this area, it's got a base of 4 seconds and a height of 20 meters per second. So our area would be 1/2 times 4 seconds times 20 meters per second, right? So 1/2 base times height. Okay, that is equal to 1/2 times 4 times 20, which would be 40 meters. Okay, so my total distance here would be 40 meters plus 160 meters. It also works out in terms of the units, right? So if I take meters per second times seconds, that would be meters per second times seconds. That just equals meters, right? So our units will be meters at the end. So my total distance equals 200 meters. Okay, cool. So that's the last new kind of problem I want to go over. I'm trying to think if there's any other review things I want to say. All right, there's none that I can think of right now. If I think of other ones, I'll post it on Google Classroom. Okay, so after you're done watching this video, you can get started on the practice test. You can either do it on AP Classroom, or you can either fill it out on the PDF on your iPad, or you can print it out and fill it out and bring it into class. But your job for Tuesday is to have gone through all those questions. If you're doing AP Classroom, then have it check it so you can see which ones you got right and which ones you got wrong. And then on Tuesday, we'll go over any of them that you've got questions on. But my expectation is that you will have looked through all of those questions and tried to answer each one of them. Not too many of them involve calculations. A lot of them are just concepts. So it shouldn't be, more than like an hour worth of time. Yeah, I'm going to record a video of an angled launch problem where you have to use the quadratic formula. That's something like number 4. I'm going to put that up online. I'd say that is sort of our least prioritized thing. So if you're interested in seeing how that works out, take a look at that video. If you're pressed for time, don't worry about that one. Just worry about doing the practice test questions. And I'll see you on Tuesday. Have a good day off.